So in the last 2 weeks, we've built an ALU and memory hierarchy, and basically we're at the stage we can just combine them and build a computer. But we're going to postpone that to next week, and this week we're going to actually look at the computer that we want to build from a user's point of view. Study what can we do with the computer that we're going to be, what exactly is the specification of the computer that we're going to build, and then only after we've looked into it, played with it, we're actually going to build it in next week. So why do we need to do that? Well, basically because the computer is a complicated thing. It can do lots of things. When you think about it, this is really amazing. Most machines that we have in the world do one thing. Your washing machine only washes clothes. It cannot cook spaghetti. On the other hand, a computer, and for that matter, a smartphone is a computer, can do lots of different things. It can do word processing. You can play games on it. You can talk with other people. It can show you videos. There are an enormous amount of stuff that the same computer does. So how is it possible that we can do all these different things with a single hardware, with a single machine? The basic idea here is that of universality. The origins of this idea were theoretical models that considered by Alan Turing in the early 19th and 20th century. He tried to formalize the notion of a computing machine and defined a theoretical model, a Turing machine, that actually tries to capture the essence of what can be computed. And then he noted this amazing phenomena. Although there are many different computing machines, many different Turing machines in his model, there was a single one of them that could actually act like all of them given the correct program. It could simulate all of them, and that is called a universal Turing machine. That was the first time we have this amazing idea of one machine acting as a huge amount of all machines. In fact, it can act as anything at any computing machine. The same idea actually was turned into practice by von Neumann, who actually built the first serious architecture of a general computing machine, where he noticed that where the centerpiece of his architecture was the fact that we had a stored program computer. We can put the program, software, inside the hardware, and then it can act in a way that is according to the software that we put there. Different programs create different operations, different functionalities. And in this way, we actually had a real computer for the first time that could perform many different functions, run many different programs. And that secret is still with us to date, and we don't even notice how remarkable it is that our single machine can do all these many different things. So let's look slightly more carefully, how does this actually work? So we have our computer. Inside the computer, we know we're going to have some central processing unit, we're going to have some memory, it's going to read some input, produce some output. But inside that memory is going to be a program that is going to tell the computer what to do. While the hardware is fixed, that program, the software, can change. And as the software changes, the computer will do different things. So let's see how does the hardware, the single hardware, static hardware, perform many things according to the program. Well, the program has a sequence of instructions. Each one of them is going to be coded in binary, and our hardware is simply go instruction by instruction and execute it. Now, different sets of instructions, different sequences of instructions will thus cause our hardware to produce completely different things. And when we take the whole program, the whole sequence of instructions together, we get the functionality of the program, which can be completely dependent on what was written there on the program itself. So now let's look at the different elements that we will need to look at more carefully, which we will do in the next unit, that together cause the hardware to do what the program wanted to do. The first thing is, how are we going to specify the instructions? Our program is going to be composed of a sequence of instructions. What exactly does the instruction tell the computer to do? That's one element. The other element is, how do we know which instruction to perform at any given stage in time? Suppose we are now in instruction 74. It makes sense that the next instruction we will do is 75, but sometimes we will need to change the order, maybe to do some kind of loops or to do things conditionally. That's the second kind of element that we need to be able to, that software needs to be able to control the operation of the hardware. The third element, which is really important, is that we're going to have to tell the hardware what to operate on. Even if the hardware knows it needs now to add two numbers, we have to tell it, the software has to tell the hardware where exactly will it get these two values that it needs to add, and where should it put the result. So these are the three basic elements, if you wish, that every machine language, every way that the hardware allows the software to tell it what to do, needs to specify. And we'll talk a little bit about possibilities and what kind of options are there for each one of these three possibilities later. Now, the point is, once we have this machine language, this is what the hardware allows the software to perform. Now, this machine language specification is really a programming language, but it's a terrible programming language. It's really convenient for the hardware. It allows specifying anything you want to do to the hardware, but it's really not convenient for human beings. So in reality, human beings never program, or almost never program, exactly in machine language, but they rather program in what's called a high-level programming language, a language that was designed for humans to be able to easily write what they want to do. And then there are automatic programs called compilers, which translate that into the machine language, into the software, which actually tells the hardware what to do when it runs it. And thus, usually, we do not worry too much about the machine language, because we as human programmers don't actually use it. However, from the computer's point of view, this is really what runs. Always only machine language programs run, and any other program that runs was really translated in some way to this machine language formalism, which is what exactly tells the hardware what to do. Even though normally people do not write in machine language, in this course, where we are actually dealing with the hardware that runs the machine and with the software that directly operates above it, and because we're really learning about this machine language in order to understand how to build the computer, we're going to have to deal directly with the machine language. And there are some other situations where people deal directly with machine language. For example, if they really want to only machine language programs run, and any other program that runs was really translated in some way to this machine language formalism, which is what exactly tells the hardware what to do. Even though normally people do not write in machine language, in this course where we are actually dealing with the hardware that runs the machine and with the software that directly operates above it, and because we're really learning about this machine language in order to understand how to build a computer, we're going to have to deal directly with the machine language. And there are some other situations where people deal directly with machine language, for example, if they really want to have highly optimized code for very specific tasks. In this case, in these cases, and in our course, we will need to pay a little. We need to make working with a machine language slightly easier. And there are two things that are normally done when working with machine language, which makes things easier. The first thing is instructions in machine language are always sequences of bits. That's how we keep all information in a computer. This is terrible because it's very difficult to program to look at an instruction 0, 1, 1, 1, 1, 1, 0 and see what it's supposed to mean. But in reality, there is some way this instruction codes something in a computer, and usually it codes something that we can understand. For example, it could be that the first part of this sequence of bits really codes add, addition. In that case, when we talk about this kind of instructions, it will be more convenient to talk about the mnemonic form of this instruction and simply say add instead of 0, 1, 1, 1, 0 or whatever the code is. Similarly, parts of the instruction may code a specific thing. For example, perhaps the second part of the instruction codes as a register that we want to use, whatever that means for now. In this case, again, we can write R2, which makes sense to humans, somehow implying the second register, rather than the sequence of bits, which really codes this too in some way, depending on the machine language. So instead of talking about this sequence of bits, which makes no sense to humans, we're going to think that what's really written there is a command add R3 to R2. And then we're going to specify exactly what that means to our computer. And this is exactly equivalent to talking about the earlier sequence of bits. It will just make things easier for us. Now, there are two ways to interpret it. The simplest way, and this is the way I prefer looking at it at the beginning of this stage, is simply that the syntactic form, the nice form, does not exist anywhere, just the way that we're talking about the real bits that exist in the computer. That's the first thing. So when I say add, I really mean 0, 1, 1, 1, 0, or whatever the machine language specifies. The second interpretation goes one step further and looks at the following thing. Well, sometimes we do want to code in machine language, and why not allow the human to actually write things in this syntactic form, in this what's called assembly language form, and then we can translate it to the bits very easily. This is what a program called an assembler does, and you will actually need to build this assembler in the 6th week. So that's the second interpretation that we will have, where there is a program that allows you to write this machine language not directly as bits, but in a slightly nicer assembly language format. While we're at it, making things a little bit easier to actually write programs in machine language for the rare cases that we need to do that, including this course, then there's another thing that we get for free, and which is called symbols. A lot of times in a machine language program, we will need to access memory locations. For example, there could be a command that tells add 1 to memory location 129. Now, the point is for the programmer writing that, it's not really need to access memory locations. For example, there could be a command that tells add 1 to memory location 129, and which is called symbols. A lot of times in a machine language program, we will need to access memory locations. For example, there could be a command that tells add 1 to memory location 129. Now, the point is for the programmer writing that, it's not really important that we actually talk about machine location, memory location 129. What he really has in mind, our programmer, is that we're going to keep some kind of index in that machine location, in that memory location. So for the programmer, this could have been instead kept at the add 1 to memory location 129. Now, the point is for the programmer writing that, it's not really important that we actually talk about machine location and memory location 129. What he really has in mind, our programmer, is that we're going to keep some kind of index in that machine location, in that memory location. So for the programmer, this could have been instead kept at the memory location 250, or a lot of times in a machine language program, we will need to access memory locations. For example, there could be a command that tells add 1 to memory location 129. Now, the point is for the programmer writing that, it's not really important that we actually talk about machine location and memory location 1. 129. We need to do that, including this course. Then there's another thing that we get for free, and which is called symbols. A lot of times in a machine language program, we will need to access memory locations. For example, there could be a command that tells add 1 to memory location 129. Now, the point is, for the programmer writing that, it's not really important that we actually talk about machine location and memory location 129. What he really has in mind, our programmer, is that we're going to keep some kind of index in that machine location, in that memory location. So for the programmer, this could have been instead kept at the program at memory location 250 or any other memory location. The important point was that every time that I'm talking, that I use this value, I go to the same memory location. In this situation, we might as well allow the user to write some kind of symbolic symbol, some kind of name for that memory location. Let's say call it index, and automatically lets our assembler that already is providing us with some convenience, allow the assembler to actually translate the word index into some free memory location, for example, 129. Again, this will allow us to write programs in easier ways to humans, that look easier to humans, without changing everything in reality. Whenever you see index, that really just means some memory location which is fixed and is used the same memory location whenever we talk about index. So this finishes the overview about the idea of machine languages. And what we're going to do in the next unit is actually talk a bit about specifics of machine languages. What kind of things do we have in them? What kind of elements are they composed of? And once we have that basically background, that perspective on what kind of machine languages, what kind of things we do in machine languages, then we'll actually start talking about the machine language of the computer that you'll build in this course, the hack computer. In the previous unit, we talked about the general idea of a machine language and how they control computers. What we want to do in this unit is discuss basic elements that appear in all machine languages. The main reason is to give you some context for what you will learn about the hack machine language in the next unit, because most of the elements that you find in the hack machine language are, of course, elements that appear in some way, in some form, in other machine languages. So we first start with a general description of the kind of elements you find in machine language. We talked about the general idea of a machine language and how they control computers. What we want to do in this unit is discuss basic elements that appear in all machine languages. The main reason is to give you some context for what you will learn about the hack machine language in the next unit, because most of the elements that you find in the hack machine language are, of course, elements that appear in some way, in some form, in other machine languages. So we first start with a general description of the kind of elements you find in machine languages, a very elementary description that is missing a lot of more sophisticated features that you find in many computers, and then you'll have this context for the hack machine language. So the first important thing to remember is, so in the last 2 weeks, we've built an ALU and memory hierarchy. And basically, we're at the stage we can just combine them and build a computer. But we're going to postpone that to next week. And this week, we're going to actually look at the computer that we want to build from a user's point of view. Study what can we do with the computer that we're going to be, what exactly is the specification of the computer that we're going to build. And then only after we've looked into it, played with it, we're actually going to build it in next week. So why do we need to do that? Well, basically because the computer is a complicated thing. It can do lots of things. When you think about it, this is really amazing. Most machines that we have in the world do one thing. Your washing machine only washes clothes. It cannot cook spaghetti. On the other hand, a computer, and for that matter, a smartphone is a computer, can do lots of different things. It can do word processing, you can play games on it, you can talk with other people, it can show you videos. There are an enormous amount of stuff that the same computer does. So how is it possible and define a huge amount of all machines besides the hardware without tells the computer what to do? Well, the hardware is fixed. That program, the software, can change. Computer. Inside the computer, we have our computer. Inside the computer, we know we're going to have some central processing unit. We're going to have some memory. It's going to read some input, produce some output. But inside that memory is going to be a program that is going to tell the computer what to do. While the hardware is fixed, that program, the software, can change. And as the program, the software changes, the computer will do different things. So let's see how does the hardware, the single hardware, static hardware, perform many things according to the program. Well, the program has a sequence of instructions. Each one of them is going to be coded in binary, and our hardware is simply go instruction by instruction and execute it. Now, different sets of instructions, different sequences of instructions will thus cause our hardware to produce completely different things. And when we take the whole program, the whole sequence of instructions together, we get the functionality of the program, which can be completely dependent on what was written there on the program itself. So now let's look at the different elements that we will need to look at more carefully, which we will do in the next unit, that together cause the hardware to do what the program wants it to do. The first thing is, how are we going to specify the instructions? Our program is going to be composed of a sequence of instructions. What exactly does the instruction tell the computer to do? That's one element. The other element is, how do we know which instruction to perform at any given stage in time? Suppose we are now in instruction 74, it makes sense that the next instruction we will do is 75, but sometimes we'll need to change the order, maybe to do some kind of loops or to do things conditionally. That's the second kind of element that we need to be able to, the software needs to be able to control the operation of the hardware. The third element, which is really important, is that we're going to have to tell the hardware what to operate on. Even if the hardware knows it needs now to add two numbers, we have to tell it, the software has to tell the hardware where exactly will it get these two values that it needs to add, and where should it put the result. So these are the three basic elements, if you wish, that every machine language, every way that the hardware allows the software to tell it what to do, needs to specify. And we'll talk a little bit about possibilities and what kind of options are there for each one of these three possibilities later. Now, the point is, once we have this machine language, this is what the hardware allows the software to what they want to do. That immediately directly 11110, which makes sense to humans. The simplest in this syntactic form, in this what's called assembly language stage, is what's really written. Similarly, for example, it could be that the first part of this sequence of bits really codes add, addition. In that case, when we talk about this kind of instructions, it will be more convenient to talk about the mnemonic form of this instruction and simply say add instead of 01110 or whatever the code is. Similarly, part of the instruction may code specific things. For example, perhaps a second part of the instruction codes as a register that we want to use, whatever that means for now. In this case, again, we can write R2, which makes sense to humans, somehow implying the second register, rather than the sequence of bits, which really codes this too in some way, depending on the machine language. So instead of talking about this sequence of bits, which makes no sense to humans, we're going to think that what's really written there is a command add R3 to R2. And then we're going to specify exactly what that means to our computer. And this is exactly equivalent to talking about the earlier sequence of bits. It will just make things easier for us. Now, there are two ways to interpret it. The simplest way, and this is the way I prefer looking at it at the beginning of this stage, is simply that the syntactic form, the nice form, does not exist anywhere, just the way that we're talking about the real bits that exist in the computer. That's the first thing. So when I say add, I really mean 0, 1, 1, 1, 0, or whatever the machine language specifies. The second interpretation goes one step further and looks at the following thing. Well, sometimes we do want to code in machine language, and why not allow the user human to actually specify, write things in this syntactic form, in this what's called assembly language form, and then we can translate it to the bits very easily. This is what in a program called an assembler does, and you will actually need to build this assembler in the 6th week. So that's the second interpretation that we will have, where there is a program that allows you to write this machine language not directly as bits, but in a slightly nicer assembly language format. While we're at it, making things a little bit easier to actually write programs in machine language for the rare cases that we need to do that, including this course, then there's another thing that we get for free, and which is called symbols. A lot of times in a machine language program, we will need to access memory locations. For example, there could be a command that tells add 1 to memory location 129. Now, the point is for the programmer writing that, it's not really important that we actually talk about machine location and memory location 129. What he really has in mind, our programmer, is that we're going to keep some kind of index in that machine location, in that memory location. So for the programmer, this could have been instead kept at the program at memory location 250 or any other memory location. The important point was that every time that I use this value, I go to the same memory location. In this situation, we might as well allow the user to write some kind of symbolic symbol, some kind of name for that memory location, let's say call it index, and automatically lets our assembler that already is providing us with some convenience, allow the assembler to actually translate that word index into some free memory location, for example, 129. Again, this will allow us to write programs in easier ways to humans, that look easier way to humans, without changing everything in reality. Whenever you see index, that really just means some memory location, which is fixed, and is used the same memory location whenever we talk about index. So this finishes the overview about the idea of machine languages. And what we're going to do in the next unit is actually talk a bit about specifics of machine languages, what kind of things do we have in them, what kind of elements are they composed of. And once we have that basically background, that perspective, and what kind of machine languages, what kind of things we do in machine languages, then we'll actually start talking about the machine language of the computer that you'll build in this course, the hack computer. So the first important thing to remember is that the machine language is the most important interface probably in the whole world of computer science. It is the interface between hardware and software. It is exactly the way that software can control the hardware. This kind of machine language needs to specify what are the operations that our hardware performs, where does it get the data that it operates on, what is the control of the operations, and so on. In principle, and usually, this kind of interface is done in an almost one-to-one correspondence with the actual hardware implementation. The idea is that the hardware is built in a way that directly corresponds to type of. In principle, and usually, this kind of interface is done in an almost one-to-one correspondence with the actual hardware implementation. The idea is that the hardware is built in a way that directly corresponds to the type of functionality that it provides to the software layer above it. This need not happen always. Sometimes you can want to provide nice functionality, even at this level, even to just so the compiler writers will be happy about the code they need to emit, and the hardware will be another layer removed from it. But we're not going to talk about it, and from first principles, basically the machine language specifies exactly the kind of thing that the hardware can do for us. Of course, when we actually go to design a machine language, the basic element is a cost-performance trade-off. The more sophisticated operations that we want to give our machine language, the more large data types or sophisticated data types that it operates on, the more costly it will be to actually build this. Costly in terms of area of silicon, costly in terms of time that the hardware actually needs to operate, and so on. Of course, in our computer, we're always taking this kind of trade-off to the simplest. We're trying to present the simplest kind of thing and not really worrying about real performance. But in any real machine, the whole thing that drives the design of the machine language is a cost-performance trade-off. So let's talk about the type of operations that our hardware can perform. Each machine language defines a set of operations, and these fall into several categories. For example, there are arithmetic operations. For example, addition of two numbers, subtraction, maybe also multiplication or division. There are logical operations, for example, taking the AND of two bits, or maybe the bitwise AND of two words. And then there are also operations that control the flow control, that tell the hardware when to jump inside the program. So these are the type of instructions that we usually will have in any machine language, and different machine languages define different sets of such operations, which may differ from each other in terms of their richness. For example, some machines may provide division as a basic operation, while other machines will decide not to do that because it's too expensive in terms of silicon, but rather the software will, of course, have to provide that functionality. Probably even more important is the question, what data types can our hardware access primitively? So there's a big difference, of course, between adding 8-bit numbers and adding 64-bit numbers. If your software program really needs arithmetic on 64-bit values, then of course hardware that performs in one operation addition of such 64-bit values will be at least 8 times faster than hardware that needs to actually implement addition of 64-bit values by a sequence of additions of 8-bit values. Similarly, some computers can also provide silicon, but rather the software will of course have to provide that functionality. Probably even more important is the question, what data types can our hardware access primitively? So there's a big difference, of course, between adding 8-bit numbers and adding 64-bit numbers. If your software program really needs arithmetic on 64-bit values, then of course hardware that performs in one operation addition of such 64-bit values will be at least 8 times faster than hardware that needs to actually implement addition of 64-bit values by a sequence of additions of 8-bit values. Similarly, some computers can also provide richer data types. For example, you may have your hardware support directly floating point operations, numbers that are not integer but rather real numbers, and deal with them, provide addition, multiplication, division of them as a basic operation. If you want to do scientific computation, which works with these kind of floating point numbers or real numbers rather than just integers, of course such machines will be much faster than machines that can only handle integers, basically. While the difference in set of operations that we've seen previously is quite obvious, the next issue is probably even more important, although slightly more subtle. And that is the question, how do we decide what data to work on? How does the hardware allow us to specify what type of data values are we going to work on? The basic problem that we have here is that what we're going to work on resides in memory. And accessing memory is an expensive operation. It's expensive in at least two related decide what data to work on. How does the hardware allow us to specify what type of data values are we going to work on? The basic problem that we have here is that what we're going to work on resides in memory. And accessing memory is an expensive operation. It's expensive in at least two related points of view. First of all, if you have a large memory, specifying what part of the memory do you want to operate on requires a large amount of just as many bits to specify it, because you need to give an address in a very large memory. And that's going to be wasteful in terms of the instruction. If I just want to say, oh, add the last two numbers, I won't be able to just do that because I will have to specify two very large addresses in order to tell the hardware what to operate on. The second element, which is closely related, is the fact that just accessing a value from a large memory takes relatively large amount of time compared to the speed of the CPU itself, of the arithmetic operations themselves. Large amount of time related is the fact that just accessing a value from a large memory takes relatively large amount of time compared to the speed of the CPU itself, of the arithmetic operations themselves. So the way to handle these two things, the way to give us good control over what type of data are we working on without requiring all these costs of specifying a large address and getting the information from a faraway place, if you wish, in terms of time, the basic solution was what's called a memory hierarchy. And this was already figured out by von Neumann when he built his first computer. The basic idea is instead of having just one large block of memory, we're going to have a whole sequence of memories that are getting bigger and bigger. The smallest memories are going to be very easy to access. First of all, because we don't have to specify a large address space because there are only going to be a very few of them. Second of all, because there are only very few of them, we can actually get the information from them very quickly. And then there are going to be slightly larger memories, usually called cache, and even larger memories, sometimes called the main memory, and maybe even larger memories that are going to sit on disk. At each time we get farther away from the arithmetic unit itself, our memory gets bigger. Accessing it becomes harder, both in terms of giving a wider address and in terms of the time we need to wait until we get a value, but we have more information there. The ways that the different levels of the memory hierarchy are handled differs according to the different levels, but what we're going to discuss now is the way that registers, the smallest memory that usually resides really inside the CPU, how we handle that. So almost every CPU has a very small amount of memory registers that are located really inside the CPU. Their type and functionality is really part of the machine language, and the main point is that since there are so few of them, addressing them requires very few bits, and getting the information of them is extremely quickly. They are built from the fastest technology available, and they are already inside the CPU, so there is no delay in getting any information from there. So what types of registers do we have? The first kind of thing that we will do with these memory location registers that are inside our CPU is just use them for data. For example, we can put numbers in them and have operations saying something like add the register 1 to register 2. In this situation, basically what will happen is the contents of register 1 will be added to the content of register 2 if that is the meaning of this operation in our machine language. So once we have a small number of registers be added to the content of register 2, if that basically what we'll have operations saying something like add registers that are inside our CPU is just use them for data. For example, we can put numbers in them, and the main point is that since there are so few of them, addressing them requires very few bits, and getting the information of them is extremely quickly. They are built from the fastest technology available, and they are already inside the CPU, so there is no delay in getting any information from there. So what types of registers do we have? The first kind of thing that we will do with these memory location registers that are inside our CPU is just use them for data. For example, we can put numbers in them and have operations saying something like add the register 1 to register 2. In this situation, basically what will happen is the contents of register 1 will be added to the content of register 2 if that is the meaning of this operation in our machine language. So once we have a small number of registers inside the CPU, we can do lots of operations on a small amount of memory very, very quickly. The second kind of things we do with these registers is use them as addresses. We can also sometimes put into one of these registers an address into main memory, which will allow us to specify which part of the bigger memory we want to access for operations that we want to access. For example, if we have an operation like store register 1 into memory address that is specified by the register called A, then what will happen is once we actually perform this operation, that number 77 will be written into the main memory. This can be an operation that takes a larger amount of time than internal operation to the CPU. But the important point is that the address into which we write this information was actually given by the A register. This is another type of usage we have for registers that are inside our main memory. Once we have this register called A, for example, if we have an operation like store register 1 into memory address that is specified by the register called A, then what will happen is once we actually perform, so once we have a small number of registers inside the CPU, we can do lots of operations on a small amount of memory very, very quickly. The second kind of things we do with these registers is use them as addresses. We can also sometimes put into one of these registers an address into main memory, which will allow us to specify which part of the bigger memory we want to access for operations that we want to access. For example, if we have an operation like store register 1 into memory address that is specified by the register called A, then what will happen is once we actually perform this operation, that number 77 will be written into the main memory. This can be an operation that takes a larger amount of time than internal operation to the CPU. But the important point is that the address into which we write this information was actually given by the A register. This is another type of usage we have for registers that are inside our main memory. Once we have these registers, now we can go back to the original question, how do we decide which data to work upon? How do we tell the computer for an operation, let's say a simple add operation, what is it supposed to operate upon? And there are a bunch of different possibilities. Here are 4 possibilities. These are sometimes called addressing modes, and some computers have other possibilities as well. Sometimes we just want to work on these registers. So for example, we can say add register 1 to register 2, and this means, of course, that the addition operation is on 2 registers. Sometimes we have direct access to memory. We can have an operation saying add register 1 to memory location 200, in which case we're telling the computer to directly address not just the register 1, but also a memory address that we just specified inside the command. Yet another possibility is what's called indirect addressing, and this is the example we had previously for using the A register, where the memory address that we access is not specified as part of the instruction, but rather is already written inside an address register that already was previously loaded inside the CPU with some correct value. And yet another possibility is that we actually have a value inside the instruction itself. For example, we can say add 73 to register 1, and 73, the constant 73, is part of the instruction. So all these are different ways we can actually tell the computer which values, which data to work on in each instruction. While we're talking about how to inside the instruction itself, for example, we can say correct value. And yet another possibility is that we actually have a value inside the instruction itself. For example, we can say add 73 to register 1, and 73, the constant 73, is part of the instruction. So all these are different ways we can actually tell the computer which values, which data to work on in each instruction. While we're talking about how to where to take the data from and where to put it, we might also add something that is usually piggybacked upon it, which is how do we deal with input and output in most machine languages. So as we all know, there are an enormous amount of input and output devices, printers and screens and various sensors and keyboards and mice and mouses and so on. So one way to actually access these input or output devices is to actually connect the registers which control them, these output devices, as part of your memory. For example, we may have a mouse that is connected in a way that whenever the user moves the mouse, the last movement is written into some kind of a register, and that register is accessible by the computer in a certain address as part of the memory. This gives us access to input and output as though we're accessing the memory itself, and of course, the software that actually deals with this, software that is usually part of the drivers in an operating system, must know exactly not only what are the addresses to which this input or output device is connected, but also how to speak with it. What does the values in what locations, what do they really mean? The final element that we wish to discuss is what's called flow control. How can we tell the hardware what instruction to execute next? So usually it's very simple. Usually if I now was in instruction 73, the next instruction will be 74. That's a normal situation. But there are situations where, of course, we need to change the flow of control and not just continue doing instructions one after another. The first reason is sometimes we just need to go back to another location, for example, doing a loop, or maybe jumping to another part of the software just because now is the time to jump to another part of the program. So this would be what sometimes is called an unconditional jump, and one of the main uses for it will actually be to do a loop. Suppose we want to actually start and do something for values 1, 2, 3, 4, 5, 6, and so on. The way we do it, we'll have some kind of register holding these values. Each time we want to add 1 to R1, let's say if that is a register that we chose to actually have this value, and then we do whatever we need to do with this new value. Now we next want to do the same thing, but with the next value of R1. The way we do it, we have to tell the computer, oh, after you do instruction number 156 in our example, don't continue to instruction 157, but go back to instruction 102, which basically adds 1 to R1, giving us the next value of R1, and then continue doing whatever you did with a new value. So this allows you to do a 56 in our example. Don't continue to instruction 157, but go back to instruction 102, which basically adds 1 to R1, giving us the next value of R1, and then continue doing whatever you did with a new value. So this allows you to do a loop, and machine languages always have some kind of capability that the software tells the hardware to do something again, or to return back, or to jump to a different direction. Notice that the actual addresses 101, 102, and 156 are not really that important. What is really important was that when we jump to address 102, we need it to be the address that we're actually meaning. So we could do this in a symbolic manner in the following way. Just give a name to important locations. For example, location at 102, I give it a name loop. And then I say jump to loop. This doesn't really change anything. This is exactly the same thing when we actually write it in bits in our machine language, but it's more convenient for humans to look at, so we'll just do that as part of the way of describing programs. Then there are other cases which we need to handle flow control, where we need to do what is sometimes called a conditional jumps. In some cases, we want to jump to another location, while in other cases, depending on, let's say, the last instruction that we performed, or according to the value of some register, or according to some other condition, in some cases, we want to jump to another location. In other cases, we just want to continue for the next instruction. And this is called a conditional jump. For example, suppose I want to do something on the absolute value of a number. So if the number is positive, I just want to do some operation on the number. But if a number is negative, I want to first turn it into to be positive and then work on the positive version of it. The way we can do that, we can have a conditional jump greater than, which means if R1 is greater than 0, I want you to jump to the label cont. This is just a number, just a name that I made up. Otherwise, just continue. This means that if we have a positive number, then we're not going to do the next instruction, the subtract instruction. But if we have a negative number, we're just going to continue directly to do the subtract instruction, which really takes R1 and negates its value, makes it positive. Now, in both cases, we are continuing with the same sequence of instructions, and now we already have in R1 anyway a positive value. So this is an example why we sometimes would need a conditional jump, and machine languages always have some kind of apparatus, some kind of way to actually instruct the hardware to do these kind of conditional jump. At this point, we've finished a very, very quick, very high level, very basic overview of the type of instructions that machine languages provide, and now we're ready to actually talk about our computer, the Hack machine language.
In the previous 2 units, we talked about machine language in general, and from this unit onward, we're going to to talk about the HEC machine language, which is the native code that we're going to use in order to operate the HEC computer. Now, I don't want to talk too much about the HEC computer itself because we're going to spend a whole week or more than 1 week talking about the computer, but I do want to give you an overview of the hardware platform on which the machine language is going to operate. As Noam described before, these two things, hardware design and machine language design, go hand in hand, and there's certain duality between them, and you have to know one in order to understand the other. So here's an overview of the computer that you're going to build from next week onward. In fact, you've been building this computer all along, but next week we're going to actually assemble all these pieces together, and we're going to have a computer which consists of three main elements. We're going to have basically, first of all, we're going to have a 16-bit computer. And a 16-bit computer is a machine in which everything consists of chunks of 16 bits. So if you want to store something, you have to store 16 bits together. If you want to retrieve a piece of data, you have to retrieve 16 bits. If you want to move data from one place to another, you move them in chunks of 16 bits. So this is the atomic unit of information in this computer. Now, the computer is going to consist of a data memory, which is a sequence of 16-bit values, and each of these values is going to be stored in a memory register, and these registers are numbered for convenience. We can think about them as register 0, register 1, all the way to as many registers as we have in the data memory. The instruction memory is a separate memory space that is also a sequence of 16-bit values, and the CPU is a device which is capable of manipulating 16-bit values using mostly the ALU, which resides inside the CPU. And finally, that is also all the way to convenience. We can think about them as register 0, register 1, and move them in chunks of 16 bits. So this is the atomic unit of information in this computer. Now, the computer is going to consist of a data memory, which is a sequence of 16-bit values, and each of these values is going to be stored in a memory register, and these registers are numbered for convenience. We can think about them as register 0, register 1, each of 16 bits. So this is the atomic unit of information in this computer. Now, the computer is going to consist of a data memory, which is a sequence of 16-bit values, and each of these values is going to be stored in a memory register, and these registers are numbered for convenience. We can think about them as register 0, register 1, all the way to as many registers as we have in the data memory. The instruction memory is a separate memory space that is also a sequence of 16-bit values, and the CPU is a device which is capable of manipulating 16-bit values using mostly the ALU, which resides inside the CPU. And finally, we're going to have all sorts of stuff from one place to another. So we have a data bus that connects the CPU and the data memory. We have an instruction bus that moves instructions from the instruction memory to the CPU. And we're going to also have some address buses, which I didn't put in the picture to avoid clutter. And also, we don't need this level of detail for this particular unit. You can think about the buses as highways of 16 lanes moving chunks of 16 bits from one place to another. All right, so how do we control this computer? Well, we have software. And the software is, in this level of the machine, the software consists of machine language, or the programs that we write using machine language. And when we designed this computer and when we designed this machine language, we decided to create two categories of instructions, which we call A instructions and C instructions, and each one of these instructions is specified as a 16-bit number, like everything else in this machine. So what is a HEC program? A HEC program is essentially a sequence of instructions, 16-bit numbers, written in the HEC, written in the HEC machine language. What about control? Well, before we talk about control, I have to introduce yet another element in this platform, which is called a reset button. So we do have a reset button, and here is how I cause this computer to do something useful for me. I write a program. The program is a set of 16-bit numbers. I take these 16-bit numbers and somehow put them into the ROM. We'll discuss later how we actually do it. Then I press the reset button, and once I do this, the program starts running. That's the basic sort of user instructions of how to cause this computer to do something useful. Now, I have no idea what the computer will do. It all depends on the program, but hopefully the computer will start sounding some music or showing a video clip or compute the average of 1 million numbers or something like this. It all depends on what is written in the program. Now, before we go on to talk about the machine language, I'd like to say a few words about some more hardware artifacts that we have to be aware of. The Hack computer recognizes 3 registers. First of all, there's the D register, which holds a 16-bit value, which represents a piece of data. Then there's the A register, which holds also a 16-bit value, which represents either a data value or an address. We'll talk about this later on. And finally, there is something called the selected memory register, which is denoted by the letter M. So it doesn't matter if I have 2 billion memory registers. At any given point of time, only one of them is selected. And I can basically ignore all the other registers. They're irrelevant for what I currently do. I want to focus only on the currently selected register, and I call this register M. This is just a convention that we use in the specification of the Hack machine language. All right, so now we have all the basic background that we need in order to understand the syntax of the language. So here's the syntax of the A instruction. Ampersand value, or at value, where value is either a non-negative decimal constant or a symbol referring to such a constant, and we'll discuss these symbols later on. Now, instead of spending too much time about the formal semantics, let's see an example. What does at 21 mean? Well, if I tell the computer at 21, 2 things happen. First of all, the A register is set to 21, and second of all, RAM of 21 becomes the selected RAM register. So we see that the A register has a very important side effect. Once you set the A register to a particular value, like 21, it automatically selects a particular register from the data memory, and this register becomes the currently selected register, what I called M in the previous slide. All right, so this is the operation that's the semantics of the A instruction. Here's an example of how we actually use this instruction. Let's say that we want to set RAM 100 to -1. How do I do it? Well, the first thing that you have to do is select the register on which we want to operate, and we do it by saying at 100. Once we do this, we get the side effect working, and then we can say M equals -1, because M now denotes register number 100 in the memory unit. So that's how we use the A instruction. We always need it before we operate on the memory. Before we do something to the memory, we have to select a register, so we always have to address the memory using an A instruction. And that's, by the way, why it's called A for addressing. The C instruction is the workhorse of the language. That's where most of the action takes place. And the syntax of this instruction consists of three different fields, which we call destination, computation, and a jump directive. Now, here's how it works. First of all, we compute something. And then we can do one of two things. We can either store the result of the computation in some destination, or we can use this computation to decide if we want to jump to some other instruction in the program. Now, this is the basic overall semantics of the C instruction. Now, let's get more into the details of every one of these fields. The computation can be any one of the computations that we see here. So we see here a set of what is sometimes called mnemonics, or symbols that represent some operation. So we can compute the values 0, 1, -1. We can compute the current value of the D register. We can compute D minus 1, D plus A, D and A, and end here is a 16-bit A, D 16-bit OR A, and so on and so forth. And wherever you see the mnemonic A, we can replace it also with a mnemonic M. So we can do many different things using the computation field. What about destination? Well, we have 8 possible destinations, beginning with null, which means that we don't want to store the results of the computation at all. And we can store the result of the computation either in the currently selected RAM register or in the D register, or interestingly enough, we can store it simultaneously both in M and in D. This is something which is actually quite powerful about the Hack machine language. We can simultaneously store the result of computations in more than one container. You know, we have 8 different possibilities, and the programmer is free to use any one of them according to what he or she wants to do. Now, what about the jump directive? The jump directive takes a little while to get used to, and here's how it works. We have 8 possible conditions, and these conditions always apply, they always compare the result of the computation to 0, okay? And once again, instead of belaboring about it, I'm going to give some examples in just a few minutes, so this will become much clearer once we see the examples. So let's say that I want to set the D register to -1. Okay, set the D register to -1. I look at the language specification, and I see that I have -1 is one of the values that I can compute, and D is one of the legible destinations, so I can simply say D equals -1. The jump directive is optional, so I don't have to specify it. So, case closed. Let's move on to the next example. Let's say that I want to set RAM 300, register number 300, to the value of the D register -1. Once again, I look at the language specification, and but before I do so, actually, I have to select the register on which I want to operate. You know, whenever I want to access the memory, I must use an A instruction to select the register of interest. So I say at 300, and then I look at the specification, and I see that I have D-1 as one of the values that the CPU can compute for me, and I have M as one of the legible destinations. So all I have to do is say M equals D-1. And that is how I set register number 300 to D-1. And as you see, I need 2 instructions to carry out this particular operation. Whenever I do something to the memory, I first have to use an A instruction to select the register on which I want to operate. Okay, the last example deals with a jump. You know, how do I tell the computer to jump to execute a particular instruction? Let's say that the condition that I want to use is that if D-1 equals 0, jump to execute the instruction which is located in ROM 56. You know, this is similar to, for example, a condition that terminates a loop. You know, I do something in a loop, and each time I check the value of D-1, and when it reaches 0, I want to jump to some other instruction. So how do I do it? Well, once again, whenever I deal with a memory, the first thing that I have to do is use an A instruction to specify which register I want to operate on. So I say at 56 to select the address 56, and then I look at the language specification. I see that I have D-1 as one of the possible computations, and I also have a JEEC, which means jump if the value of the computation equals 0. And that's exactly what I want to do, right? I want to jump if the value of d minus 1 equals 0. So I compute d minus 1, and I say j_eq. So if the value of d minus 1 equals 0, jump. Instead of equals, I could have used greater than, less than, not equal, and so on. And notice, by the way, that I also have an unconditional jump. If I simply want to jump to 56 without checking any condition, all I have to say is jump. And in fact, if I want to be more accurate, the syntax that we have in this language requires that I say 0, semicolon, jump. Now, this is just a convention. So if I want to do an unconditional jump, I do 0, semicolon, JMP, and this will cause an unconditional jump. By the way, everything that I say here is described semicolon, jump. Now, this is just a convention that I also have an unconditional jump. If I simply want to jump to 56 without checking any condition, all I have to say is jump. And in fact, if I want to be more accurate, the syntax that we have in this language requires that I say 0, semicolon, jump. Now, this is just a convention. So if I want to do an unconditional jump, I do 0, semicolon, JMP, and this will cause an unconditional jump. By the way, everything that I say here is described fully in the book and in the website, so you don't really have to remember any one of the details because you can refer to them later on. So this has been an overall description of the Hack computer language. And in the next unit, we're going to be more specific about this language because we're going to describe two different flavors of this language. What we've seen so far was the symbolic flavor of the language, but we can also write all these instructions using binary codes. And it's quite interesting to see how these two flavors relate to each other. We'll do this in the next unit. In this unit, we're going to complete the description and the specification of the Hack machine language. So once again, the overall context is that we have a hardware platform consisting of a instruction memory, CPU, and a data memory, and we have a machine language consisting of A instructions and C instructions. We described these instructions in the previous unit. And a Hack program is a sequence of such instructions batched together, and we execute them one at a time. That's the overall picture. Now, as it turns out, and this is true for every machine language out there, you can write programs in machine language using two different flavors, or two different languages, if you will. You can write them symbolically, using mnemonics and friendly symbols, and that's what we see here on the left-hand side at the bottom of the slide, or you can write them using agreed-upon binary codes. Now, if you write programs symbolically, you need someone to translate these programs from symbols to binary code, and once you do this, once the program is specified in binary codes, you can actually take this code, load it into the computer, and actually execute the code on the computer. Now, we're going to spend a whole week talking about this translation and about a very special program called an assembler. So I'm not going to spend too much time discussing the translation process, but I just want you to know that it's a challenge that has to be met somewhere when you build this computer. So here is the symbolic and binary syntax of the A instruction. Well, the symbolic syntax is something that we've seen before, at certain value. And this value can be either a number, which is at most 2 raised to the power of 15 minus 1. You may be wondering where this number comes from, and you'll see it in just a minute. Or it may be a symbol which refers to such number, and we're going to defer the discussion of symbols to a later unit. For example, at 21. So here's the same instruction in its binary flavor. We begin with a special code 0, which tells the computer that this is an A instruction. And then we specify the same value that we had in the symbolic instruction, but we specify it using binary code. So altogether, we get something like this example here. Once again, the first 0 is sometimes called an opcode, an operation code. And then come 15 bits that represent the value that we want to load into the A register. And it so happens that hopefully 10101 is the same as 21 in binary. What about the C instruction? Well, the C instruction, as you recall, the symbolic definition of the C instruction is very user-friendly. We have a computation, which we can store in a certain destination, and we have an optional jump directive, and that's the great benefit of symbolic expression. If we want to express it in binary, then we have to decide on some agreed-upon codes, and Noam and I have already done that when we designed this language. So here is the 16-bit specification of the same symbolic instruction. The first one is an opcode. It tells the computer that this is a C instruction. If you recall, we have only 2 types of instruction, A instruction and C instruction, and that's why we need only one code or one bit to represent the opcode, which is either 0 or 1. So one opcode means this is a C instruction. Then we have 2 bits which we don't use. We don't need them, and by convention, we set them to 1. The next 7 bits taken together specify what is the computation that I want to achieve. These are the control bits that will be sent later on to the ALU and will tell the ALU which computation it has to carry out. The next 3 bits represent the destination, and finally, the last 3 bits represent the jump condition we code symbolically using the word jump. So this is the sort of the different fields of the instruction in its binary flavor. So let us discuss now the mapping between the symbolic expression of the C instruction and the binary expression of the same instruction. Let us begin with the comp field. So here's a table that relates the symbolic computation mnemonic to their binary equivalents. what we see on the left-hand side is the symbols, and on the right-hand side we see the binary codes, and we also have the A bit that you can see at the bottom of the table. So, for example, suppose that the computation is d plus 1. Symbolically, we want to cause the computer to compute d plus 1. Well, we look up the table, we see the d plus 1 somewhere in the middle of the table, and we see that the d plus 1 is listed in the column where a equals 0. So we know that the a bit should be 0. Then we look up the rest of the row in this table, and we see that the c bits should be 0, 1, 1, 1, 1, 1. So that's it. That's how we represent the operation d plus 1 in binary. It's 0, 0, 0, or whatever it is. I don't want to make a mistake. You just look up the table and you have it. So that's how you map from symbols to binary codes. Okay, moving along, let's talk about the destination field. A very similar idea. We have a mapping that gives you the symbolic mnemonics on the left-hand side, and in the next column you have their binary code equivalents, which very conveniently range from 000 to 111, because we have 8 different possible destinations. So once again, if someone gives you a particular destination like MD, you look it up in the table, and immediately you see that it relates to the binary code, in this example, 011. So that's how you can translate from symbols to binary code if you have to. All right, finally, let us focus on the jump field, almost the same as the destination. We have exactly the same concept. We have the mnemonics on the left-hand side, and we have 8 different possible binary combinations in the next column. Once again, conveniently enough, we have 8 different jump conditions, and therefore their binary equivalents, conveniently enough, range from 000 to 111. So that's it. This basically sums up the mapping between the symbols and the binary codes. If we want to put it all together, we can do it in one slide. And this is a complete specification of the C instruction in all its glory, both in the symbolic rendition and in the binary rendition. And if you had to write a computer program to translate from one language to the other, you can begin to see how you can use this logic in order to write this program. And by the way, this is something that we're going to do in the last week of this course. So now that we understand how the specific instructions look like in both binary and symbolic, let's move on and talk about the overall concept of a hack program. Here's an example of a hack program. At this level of the course, you don't have to understand the program. We're just giving you a first overview of how a program looks like, and we can make some quick observations. First of all, a hack program is a sequence of hack instructions. This program is written using symbolic instructions. White space is permitted. You can throw in empty lines wherever you want if you think that it improves the readability of the program. And comments are welcome and can be used at
database, proud space, 64-bit numbers. If your software program really needs arithmetic on 60 faster, right? Few of them. Sometimes, and one of the main uses for it will be to do a loop. Suppose we want to we need to handle flow control where we need always
too much about all along, but values, which how they're capable of manipulating 16-bit values using more in the picture A instructions and C instructions of the machine, moving chunks of 16. We designed this computer, and when we designed this machine language, we decided to create two categories of instructions, which we call A instructions and C instructions, and each one of these instructions is specified as a 16-bit number, like everything else in this machine. So what is a hack program? A hack program is essentially in the hack code. Written in the hack machine language. To introduce yet another, I write the 16-bit numbers actually do the views now showing a video clip or a million numbers. We'll say a few words about some more, talk about this compute in the program. Now, before we go on to talk about the machine language, I'd like to say a few words about some more hardware artifacts that we have to be aware of. The hack computer recognizes three registers. First of all, there's the D register, which holds a 16-bit value, which represents a piece of data. Then there's the A register, which holds also a 16-bit value, which represents either a data value or an address. We'll talk about this later on. And finally, there is something called the selected bit value, which represents artifacts that we have to be aware of. The hack computer recognizes three registers. First of all, there's the D register, which holds a 16-bit value, which represents a piece of data. Then there's the A register, which holds also a 16-bit value, which represents either a data value or an address. We'll talk about this later on. And finally, there is something called the selected memory register, which is denoted by the letter M. So it doesn't matter if I have 2 billion memory registers. At any given point of time, only one of them is selected. And I can basically ignore all the other registers. They're irrelevant for what I currently do. I want to focus only on the currently selected register, and I call this register M. This is just a convention that we use in the specification of the hack machine language. All right, so now we have all the basic background that we need referring to such a constant, and we'll discuss these symbols later on. Now, instead of 21, become -1. Syntax over in the currently selected RAM register, or in the D register, or into will. And finally, I'd like to say that this is not a great way to write hack code. There are better ways to write code with less numbers and more symbols, and this is something that we'll do later on in the course. Once again, for now, I just want you to see an example of a typical hack program. And if we want to run this program on the computer, we first of all must translate it into binary code. So we have either a human assembler or a computer program that translates from one to the other. Once the program is expressed in binary code, we can actually load it into the computer and execute it, and the program will hopefully do something useful. If not, we can go back, debug the program, recompile it or reassemble it, rerun it, and so on until we're satisfied with it. So this has been the last unit in which we talked about the hack machine language, and in the next unit we are going to talk about how we can use this language to control input-output devices which are connected to this to the hack computer. As we all know, computers are equipped with all sorts of input-output devices, and likewise, the hack computer can also be connected to some input-output devices. And in this unit, we're going to talk about how we use machine language to control and manipulate these I/O devices. So we start with the basic architecture that we've seen all along, but now we're going to extend this architecture with two fancy I/O devices. We're going to have a display unit similar to your screen, and we're going to have a keyboard which is actually identical to the keyboard that you are currently using. These devices are sometimes called peripheral because, as you see in the picture, they exist outside the computer. They exist somewhere in the periphery of the computer. And here is how we actually use them. Well, obviously, we use the I/O devices in order to communicate with the user. We show some pictures or animations or anything that we want to show to the user using the display unit, and we acquire inputs from the user using the keyboard. Now, obviously, we have some more devices like mouse and microphones and so on, but for now, let us talk only about the two sort of most important device units, which are the display unit and the keyboard. How do you control these devices? Well, if you're lucky to work in a high-level environment, if you use languages like Java or Python, well, in that case, you have numerous libraries that provide all sorts of fancy way to manipulate these devices. You can create graphics, animation, audio, video, and so on. However, if you work at the low level that we are operating on, the only thing that you have is bits. So you have to be very clever about it, and you have to figure out a way to use these very Spartan zeros and ones in order to do something useful and display and acquire information from users and to users. Now, you may be wondering, how do we use the high level in order to manipulate I/O devices? Because this is also something that we have to learn and understand how these libraries work. How do you draw a line? How do you draw a circle? And so on. Well, this is something that we deal with in the second part of this course. So if you want to learn about the software hierarchy, if you want to learn about the design of high-level languages and the I/O libraries that extend them and how they operate also, how they communicate with the operating system, this is something that we do in the second part of this course. In this part of the course, we deal with the hardware only. So once again, in this course, we're going to talk about the very clever ways in which we use bits to manipulate these devices. So the first thing that we'll talk about is how to manipulate the output, or how to manipulate the display unit, also called screen sometimes. Well, how do you do it? Well, the most important player in this game is something called a screen memory map. And the screen memory map is a designated area which is part of the data memory, of what we sometimes call RAM. So the deal is such that the physical display unit is continuously refreshed from the contents of the memory map. And this happens many times each second. So if I'm a programmer and I'm restricted to working with zeros and ones only, if I want to write something on the display unit, what I can do is simply manipulate some bits in the memory map, and I can count on the fact that in the next refresh cycle, what I change in the memory is going to be reflected on the screen. Now, obviously, I have to be very careful about it, and if I want to write a text like hello world, well, it's going to take a lot of work. I have to turn on and off pixels in very specific locations in order to affect this particular output. So we'll do some of this today, and we'll do some more fancy input-output operations, some much more fancy operations in the second part of this course, as I explained earlier. All right, so let's delve into the screen memory map. Now, this is how we are used to think about display units, but as far as the hack computer is concerned, the display unit is the following abstraction. It's a table or a matrix consisting of 256 rows and 512 columns. And in each intersection of a row and a column, we have what is known as a pixel. This is a black and white screen, so we can either turn the pixel on or we can turn it off. This is the physical display unit that the hack computer assumes. Now, how do we control it? Well, as I just explained, we have something called a memory map, and the memory map is a sequence of 16-bit values. Every one of these values is sometimes called a word. So we have altogether 8K 16-bit words. Why do we have 8K 16-bit words? Because it turns out that 8K times 16 gives something like 13,000 and something, and this is the number of pixels that we have on the physical display unit. So for every pixel on the physical display, 8K 16-bit words, because it turns out that 8K times 16 gives something like 13,000 and values. Now, how do we control it? Well, as I just explained, we have something called a memory map, and the memory map is a sequence of 16-bit values. Every one of these values is sometimes called a word. So we have altogether 8K 16-bit words. Why do we have 8K 16-bit words? Because it turns out that 8K times 16 gives something like 13,000 and something, and this is the number of pixels that we have. Every one of these values is sometimes... Now, how do we control it? Well, as I just explained, we have something called a memory map, and the memory map is a sequence of 16-bit values. Every one of these values is sometimes called a word. So we have altogether 8K 16-bit words. Why do we have 8K 16-bit words? Because it turns out that 8K times 16 gives something like 13,000 and something, and this is the number of pixels that we have on the physical display unit. So for every pixel on the physical display unit, we have a bit that represents this pixel in the screen memory map, and if I want to turn on this pixel, I put 1 in this bit. If I want to turn it off, I put 0 in this bit. So in order to understand and control these bits judiciously, I have to come up with some mapping that describes exactly which bit corresponds to which pixel. Now this is a little bit involved because on the right-hand side I have a two-dimensional abstraction, and on the left-hand side I have a one-dimensional abstraction, and I somehow have to connect the two. So how do we do it? Well, first of all, you should notice, and I'd like to re-emphasize the fact that when we access memory, we can only retrieve 16 bits in one chunk. You know, we cannot access individual bits. If I want to access an individual bit, I have to figure out, first of all, in which word this bit resides, so to speak, and then I have to retrieve the entire word, do something to this value, and manipulate this particular bit, and then I have to take this value and put it back, write it back into memory. So the read-write operations are always 16-bit operations. So I take the 16-bit out, manipulate something, and put it back. All right? So what is the mapping? Well, here it is. The first 32 words in the memory map correspond to the first row in the display unit. Okay, so the first pixel that we see here, and actually you can see it in the picture. We see that the picture begins with 4 black pixels, and indeed we see 4 ones at the top of the memory. Then we have 0, 1, 0, 1, white, black, and so on and so forth. Okay, so that's row 0. Then we have row 1 all the way down to row 255. Okay, so this is the first mapping that we have to bear in mind. Now, suppose that I want to manipulate a certain pixel on the screen, and pixels on the screen are characterized by a row and a column. How do I map this row-column pair on the right register in the memory map? Well, here's how I do it. Well, first of all, I multiply row by 32, and then I compute column divided by 16. And this, by the way, is integer division, name column pair on the right register in the memory map. Well, here's how I do it. Well, first of all, I multiply row by 32, and then I compute column divided by 16. And this, by the way, is integer division. Namely, I throw away the remainder of the division. So for example, if column equals 18, then 18 divided by 16 is 1. So I take the result of this integer division, I add it up to 32 times row, and this gives me the address of the register that I have to manipulate in the respective memory map. Now, notice the word screen. What does screen means here? Well, in the Hack architecture, and in this course, we are going to implement the screen memory map using a chip called screen. So we're going to have an 8K chip called screen, which behaves exactly as a memory unit. You can retrieve data from it, you can write data into it, and this chip will serve as our memory map. However, when we build the overall computer, this chip is going to be part of the data memory. So the data memory, or the RAM, will consist of several chips, and the screen will be one of them. That's exactly how we described it before. We said that the memory map is part of the data memory. But notice that once you take this screen chip and put it in a larger memory context, the base address of the memory map changes. So if I access the screen chip, I use the address that you see here. But if I access the overall RAM, I have to take this relative address and add to it the base address of the memory map in the overall memory, which happens to be 16384. So this is just technical detail. If you want to manipulate 855. Okay, so this is the first on the screen, and pixels that I want to manipulate a certain row. What is screen? The remainder of the division. So for example, if I compute pixel on the screen, and pixels on the screen are characterized by a row and a column. How do I map this row-column pair on the right register in the memory map? Well, here's how I do it. Well, first of all, I multiply row by 32, and then I compute column divided by 16. And this, by the way, is integer division. Namely, I throw away the remainder of the division. So for example, if column equals 18, then 18 divided by 16 is 1. So I take the result of this integer division, I add it up to 32 times row, and this gives me the address of the register that I have to manipulate in the respective memory map. Now, notice the word screen. What does screen means here? Well, in the HACK architecture, and in this course, we are going to implement the screen memory map using a chip called screen. So we're going to have an 8K chip called screen, which behaves exactly as a memory unit. You can retrieve data from it, you can write data into it, and this chip will serve as our memory map. However, when we build the overall computer, this chip is going to be part of the data memory. So the data memory, or the RAM, will consist of several chips, and the screen will be one of them. That's exactly how we described it before. We said that the memory map is part of the data memory. But notice that once you take this screen chip and put it in a larger memory context, the base address of the memory map changes. So if I access the screen chip, I use the address that you see here. But if I access the overall RAM, I have to take this relative address and add to it the base address of the memory map in the overall memory, which happens to be 16384. So this is just a technical detail. If you want to write to the screen using the screen chip directly, you use the first algebraic expression, and if you want to, if you are told that the screen is part of a larger memory, you have to add up the base address. All right, so we have this 16-bit word, and then we want to manipulate a particular bit inside it. Which bit is it? Well, it turns out that this bit is the column modulo 16. It's the remainder which remains after we divide column by 16. So we get a number which is between 0 and 15. We manipulate this bit, we turn it to 0 or to 1. We take the resulting value and we write it back into the RAM. Okay, if we won't do it, we won't achieve anything, right? We have to somehow write it back into the memory map, and in the next refresh cycle, what we just did is going to change the pixel in the outside display. I guess that some of you are kind of shocked at how much work it takes to turn on or off one pixel, but that's it. That's the reality. You know, if you work in a very low level, in the level of bits, that's what you have to do in order to control the screen. Now, I didn't work out all the algebra. This is something that you can do on your own. It will take a few minutes if you want, but you can just take an example. Let's say that you want to change the bit in the fourth row and in column number 55. Work out the numbers and convince yourself that you're going to access the right bit in the memory. Mm-hmm. Uh, Once again, I want to emphasize that 1 and 3, the fetching the value and writing the value back, are regular RAM operations, read, write, and we discussed it before when we talked about memory units in general. Okay, now I also want to give you an example of how this thing actually works inside our hardware simulator. So I'd like to load the screen chip into the hardware memory, manipulate it, and you can see in your own eyes how it's going to actually change the screen and manipulate the pixels. So let us load the built-in screen chip. So we look for a screen, and here it is. Loaded it. I can inspect the HDL code and see that indeed the screen chip is a built-in chip, and it's a memory chip. And if I look at the input pins and the output pins, I see that it has the typical memory chip interface. It has an input and output, a load bit that must be asserted before write operations, and it has an And here it is. Loaded it. I can inspect the HDL code and see that indeed the screen chip is a built-in chip. And it's a memory chip. And if I look at the input pins and the output pins, I see that it has the typical memory chip interface. It has an in input, an out output, a load bit that must be asserted before write operations, and it has an address that enables me to select the register on which I want to operate. Well, another thing that we can observe is that the screen built-in chip has a GUI side effect, which is this panel here, which represents or simulates a physical screen consisting of 512 columns and 256 rows. And every one of these rows is represented in the screen memory chip by 32 registers, as we explained in the lecture. So let's say that we want to turn the first 16 pixels of row number 3 to black. So in order to do this, we have to get to the register that represents the first 16 bits in row number 3. So we do 32 times 3, which gives us 96. This is the address that we have to manipulate. So we write 96 in the address input. We assert the load bit because we're going to write something into the memory. And we have to write 1111 16 times. And it turns out that 1111 16 times in decimal and 2's complement is -1. If you're not convinced, we can turn the representation to binary, and we see that indeed we got 16 ones. Let's turn it back into decimal, which is easier to read. And we see that it's very nice that we entered all these values into the memory, but we haven't ran the clock, so nothing really happened. This is a memory device. So let's run the clock. And we see that once we run it, we get two things happen. First of all, the memory now contains this value in address number 96, but also we have the side effect of seeing 16 black pixels at the beginning of row number 3 in the physical screen. Now, let us write some other arbitrary value in some other arbitrary address in the screen. So we go to the address input, we pick up some arbitrary address like 3035, and let's pick up some arbitrary value like 17 that we want to write into this address. And I'm not sure how many ones we have in 17. Let's turn the binary on, and we see that we have only 2 ones, so this is not going to be extremely visible. But in any rate, let's run the clock. And indeed, we see that these 2 babies popped up right in the middle of some obscure screen location, which happens to correspond to the register that we manipulated in the screen memory map. So these 2 pixels obviously correspond to the 2 ones that happen to be the only 2 1 bits in the binary representation of 17. So this has been a demo of manipulating the physical screen using the respective memory map, the screen chip that controls it. So the next thing that I want to talk about is the input unit. How do we control and manipulate the keyboard? Well, the physical keyboard is connected to the computer using a cable. If you will trace this cable, you will see that it goes into an area in the RAM which is called keyboard memory map. Just like we had a screen memory map, we also have a keyboard memory map, and this is the representative of the keyboard inside the computer architecture. Now, it turns out that in order to represent the keyboard, you don't need more than 16 bits. So the keyboard memory map is a single register, 16-bit register, which is called keyboard. And this is how the connection works. We have a special chip called keyboard, which once again is simply a 16-bit register. And in the next few minutes, I'm going to describe how this thing actually works. So we'll do it using examples. When a key is pressed on the keyboard, the key's scan code, which is an agreed upon value, travels through the cable and appears in the keyboard memory map. For example, if I press K, there is an agreed upon value, which happens to be 75, completely, well, not exactly, but almost an arbitrary value. And this value, 75, is going to appear in its binary manifestation in the keyboard chip. All right, I take my finger off and I click something else, like 4. Well, 4, it's true that it's a number, but on the keyboard it's yet another symbol. So the scan code of 4 happens to be 52. So if I click 4, I see the number 52 appearing in the keyboard memory map. If I click space, well, space is yet another symbol. I see the number 32 appearing there. If I click up arrow, it's yet another symbol. I see the number 131, and so on and so forth. Every key on the keyboard has a scan key which represents this selection inside the computer using a binary code. All right, so what we have here is the complete character set of the hack computer. These are the keys that the hack computer recognizes. It's a subset of the keys that you have on your regular keyboard, but it's sufficiently rich subset for our own purposes. Obviously, we could have represented all the other keys, but we decided to represent a subset of keys only. And by the way, if you have 16-bit, you can represent numerous keys and letters in many different languages, and it's more than enough. Those of you who are familiar with the notion of Unicode or ASCII can make the connection between these notions and what we do here. It's essentially the very same idea. And by the way, when you don't touch the keyboard, when the keyboard is idle, the number that we see in the memory map is 0. So that's how we can tell if the keyboard is actually being used. The memory map, once again, is this 16-bit register. And if you want to check if which key is currently pressed, all we have to do is probe the contents of the keyboard chip. In the hack computer, we probe the contents of RAM in address 24576 because this is where the keyboard memory map happens to reside. That is, when we are going to build the overall computer, we'll do it next week, we're going to connect several chips together. We're going to begin with some regular memory units, and then we're going to add to it the screen memory chip, and finally we're going to add the keyboard. And the keyboard in this overall address space is going to be located in address 24576. So if I want to know if someone is pressing the keyboard, I have to look up the value of this particular memory register. If the register contains 0, no key is pressed. If the register contains some other number, well, I can tell which key was pressed according to the scan code, according to this number. So to make this thing more vivid, I'd like to give you a demonstration of how your physical keyboard is connected to the hack computer through this keyboard memory map. So that's what we'll do next. Let us load the built-in keyboard chip. And here it is. Let's take a look at the HDL code, and we see that indeed keyboard is a built-in chip. And if we look at the chip interface, we see that it's a read-only chip. It has no input pins at all. It has only one output, which emits the value that is currently stored in the keyboard chip. Now, this keyboard chip also has a side effect, which is that the keyboard chip is connected to the actual keyboard that I'm using on my computer, on my real computer. And so will be the setting at your end. If you use our hardware simulator, the hardware simulator is connected to your physical regular keyboard. And if you touch the keyboard, if you press any key on the keyboard, the scan code of this key is going to be emitted by the built-in keyboard chip. So let us test this. And I'm taking my finger now, and I'm pressing the key G, and nothing happens. Well, nothing happens because I have to enable the keyboard, so I do it by clicking this button here. So now let us click G, and I'm holding my finger down, and as long as I hold my finger down, I will see the scan code of G, which happens to be 71, emitted by the built-in keyboard chip, which acts as the keyboard memory map. So I'm lifting my finger now, and as you see, the keyboard chip now emits the value 0, which means that none of the keys of the keyboard are presently pressed. Let's try another key. I'm going to press space. So pressing space, and I see that the scan code of space, which happens to be 32, appears. Let me press down arrow, and down arrow happens to be 133. Let us press a digit, say 8, and 8 happens to be associated with a scan code of 56, and so on and so forth. So this has been a demonstration of how we can figure out which key the user is currently pressing on the keyboard. And once again, recall that if the user is not pressing anything, we're going to see 0. So this has been the unit in which we broadened our perspective, so to speak, and added input-output units to the computer. And the most important part of this unit was to give you an idea of how you, as a programmer, can actually control these input-output units. Now that you are familiar with the Hack programming language, it's time to see what we can actually do with this language. And so in the next 3 units, we're going to talk about the general subject of low-level programming, and in particular, programming in the Hack machine language. Now, before we get started, I'd like to give you an overview of the 2 instructions that we have in the Hack language. So we have the A instruction, which is used to set the value of the A register to a particular value. And we have the C instruction, which is used to do 3 different things. We can compute a certain expression. We can store the value of this computation in some destination. And optionally, we can, based on the value of this computation, we can decide to jump and execute something which exists in a different region of the program. We can perform a go-to operation. Now, this language, as you clearly see in this slide, is symbolic. It consists of mnemonics. And computers don't understand symbols other than 0 and 1. And therefore, before we can execute anything which is written in symbolic Hack machine language, we have to first translate it into binary code. And this is something which is typically done by a program called assembler. And what we see here is this program in action. It takes a file which is written in symbolic language, and it translates it into another file written in also in symbols, but these symbols are only zeros and ones. Having produced the target code in binary code, we can actually take this file, load it into the Hack computer, and finally execute the intended program. So this is the Hack assembler, and in week 6 of this course, we will actually build such an assembler. But for now, I just want you to remember that it is available to you if you want to use it. The other option of translating symbolic programs into binary code is to use the supplied CPU emulator. You can take any program that you write in a symbolic Hack language, load it directly as is into the CPU emulator. And the CPU emulator is just it's a Java program, and it has an icon that allows you binary code is to use the supplied CPU emulator. You can take any program that you write in a symbolic Hack language, load it directly as is into the CPU emulator. And the CPU emulator is just it's a Java program, and it has an icon that allows you to load files into the instruction memory. As you load these files into the instruction memory, the CPU emulator gives you this very nice service of translating the programs on the fly into machine language. So once this happens, you can actually execute the program in the CPU emulator, and the result is that the CPU emulator is a very friendly tool for debugging and executing Hack programs in simulation. And therefore, we recommend that if you want to play with the code snippets that you will see in the subsequent units, we recommend that you do it using the supplied CPU emulator. All right, so moving along, what do we mean when we talk about low-level programming? Well, surprisingly enough, we mean a whole bunch of issues that you find in any programming language. Things like working with memory and variables and branching, iteration, pointers, inputs and outputs. These idioms are widely used in any programming language, and the Hack machine language is no exception. So in this unit, we'll begin to talk about registers and memory, and in subsequent units, we'll talk about the other subjects, which are slightly more advanced. All right, so registers and memory is the bread and butter of low-level programs, and that's what you do all the time. You manipulate registers, which are either the 2 standard registers that we have, D and A, which reside inside the CPU. If you recall, the data register can hold a single 16-bit value. The A register can hold either a data value or an address, depending in the context in which the programmer wants to use this register. And finally, we use the letter M, or the mnemonic M, to refer to the currently selected memory register. If you recall, the A register has this nice side effect that when you load it with a particular value, it ends up selecting one register from the RAM. This register in our language is called M. So we can then say something like M equals -1 or M equals 0, and so on and so forth. All right, so these are the registers of interest that we're going to manipulate, and here are some examples of what actually can be done with these registers. Let us assume that you want to store the number 10 in register D. Well, it turns out that there's no direct way to do it. If you look up the language documentation, there's no C instruction that lets you do something like that. So we have to do it indirectly. And what we do is we set the A register to 10, and then we say D equals registers. Let us assume that you want to store the number 10 in register D. Well, it turns out that there's no direct way to do it. If you look up the language documentation, there's no C instruction that lets you do something like that. So we have to do it indirectly. And what we do is we set the A register to 10, and then we say D equals A. Simple. Moving along, what about incrementing the value of D? Well, it turns out that this actually can be done directly in one instruction only, because once again, if you look up the documentation of the C instruction, you will see that you can tell the ALU to compute the value of D plus 1, and then you can take the result and store it in D. So effectively, we perform a D++ operation. What about setting D to the value of RAM 17? Well, whenever you want to access a particular memory register, you first have to address the memory. You have to select this register. So we preempt this instruction. You will see that you can tell the ALU to compute the value of D plus 1, and then you can take the result and store it in D. So effectively, we perform a D++ operation. What about setting D to the value of RAM 17? Well, whenever you want to access a particular memory register, you first have to address the memory. You have to select this register. So we preempt this operation with an @17. And now, having selected the register of interest, we set D to the value of this register. Likewise, we can do the reverse operation. We can do RAM 17 equals D, and we do exactly the same, but in reverse. Moving along, what about setting RAM 17 to 10? Well, I can do this using a combination of what I did before. First of all, I acquire the constant 10 somehow, using these two instructions, and then I set RAM 17 to the value of D, which by now is 10. What about setting RAM 3 to RAM 5? Well, once again, we can do it using similar operations, and if you want, you can stop the video, take another look at this, at all these 5 code examples, and convince yourself that they do what they intend to do. All right, so let us take these memory manipulation operations and registers manipulations and put them in the context of an actual program. So here's a program which is designed to take two values which are stored in RAM 0 and RAM 1, add them up, and save the result in RAM 2. Now, why these particular 3 words, RAM 0, 1, and 2? Well, this is an arbitrary choice. We just decided that we'll use the first 2 words in the memory for input, so to speak, and the third memory word for the output of this program. So how do we do it? Well, you may have guessed, we use very similar operations to what we did before. And if we run this program, hopefully it will compute the sum of RAM 0 and RAM 1. Now, before we go on, I'd like to remind you that instructions in the hack language have implicit line numbers. You don't see them when you write the program, but these numbers kind of lurk in the background. And when you translate this program and load it into memory, there's some interesting observations that we have to make. First of all, white space is ignored. And the only instructions that get into play, so to speak, are the real instructions, the instructions that have line numbers in this example here. And in addition, it's important to remember that what we see here in the instruction memory is a symbolic view of this program. This program as such cannot execute on the computer because the computer cannot handle symbols other than 0 and 1. But if you played with our CPU emulator, you know that you can tell the emulator to show you the contents of the instruction memory in binary. And if you do it, you will see the program in this manifestation. And in this state, the program can actually execute on the computer. But typically, once again, it's much easier to think about the program, talk about it, and debug it when the program is written in symbolic form. And therefore, we recommend that when you try to understand what a program is doing, do it symbolically. And only when you're ready to run it, if you want, you can take a look at the binary code. But it's very difficult to decode what the binary code is doing anything. So we are fortunate to have all these symbols to make our programs more readable. All right, so with that in mind, I'd like to invoke the CPU emulator and give you a demo of how this program is actually executing. So the purpose of this demo is to illustrate how to write a little program in the hack symbolic language and then run it on the CPU emulator. So I have two windows opened up here. One is the CPU emulator in the foreground, and in the background I have a simple text editor that I can use to write my program. So let's write it. We'll begin with some comments which describe what this program is doing. So let's say adds up two numbers, and let's give some usage advice to the person who is going to use this program. Put the values that you wish to add in RAM 2, in RAM 0 and RAM 1. And let's add here some more information. RAM 2 becomes RAM 0 plus RAM 1. All right, very nice. So let us begin to write the program. I use some indentation for purposes that will become clear in subsequent units. So I do at 0, d equals m. At 1, d equals d plus m. And now we can put the result in 2, m equals d. And that's the end of the program. Let's save the program using something that you cannot see now because it's far away on the screen. So we want to save the program. We'll give it the most imaginative name, demo.asm. We save it. And now we can go back to the CPU emulator and load the program. So I click the load button, and let's see. I should have a directory called program examples, and here it is. And demo is right here. So I pick demo. I load it, and here's the program that I wrote. Now, notice that the program contains only the real instructions. If you go back to the source, we see that we have, comments, white space, and so on. So when you load a program into the emulator, you get to see, or actually the only the only lines that get loaded, so to speak, are the real instructions. And as these instructions are being loaded into this GUI here, they're also being translated into machine language. And I can see that if I change the representation here to binary, and I see the program as it really is inside the ROM in binary code. But once again, it's much more convenient to see this program in symbolic code. Okay, so I was told that I have to put some values in 0 and 1, so I go ahead and put the value 5 here and 7 there. And then I begin to run the program. So let's see. We execute the first command, and we see that nothing happens yet, but A became 0. And then we do D equals M, and we see that the D register now contains 5, which is very nice indeed. Then we do at1, and we see that A contains 1. Let's do D equals D plus M. We see that D became 12. Then we set A to 2. We do M equals D, and we see that, lo and behold, RAM2 contains 12, which is exactly what we wanted to get. So the program seems to be working. Before we end this demonstration, I would like to present the fast-forward control and also use this opportunity to show you something bizarre that may happen if you don't take proper action. So I have loaded the same program into the simulator, and now I'm using different test values, 350 and minus 40, and then I will use the fast-forward control to run the program unattended, so to speak. And we see that the program runs properly, and in fact it comes out with the right result. 350 plus minus 40 is indeed 310, but we see that the computer is continuing to execute the so-called program, where in fact the program has ended already, right? As far as we are concerned, the program is ended, but as far as the computer is concerned, the program actually continues, and it seems that things are getting out of control. So having seen the demo that we just went through, and having seen also the problem that we encountered at the end of this demo, let us see what can we do in order to terminate a program properly. Now, to remind you, the problem that we had is that the flow of control became kind of uncontrollable. And basically, we told the computer to execute every instruction, everything was just fine, but then other so-called instructions came into play, and the computer basically went out of control. Now, if I were a hacker, if I were a bad hacker, and I would have seen this pattern of execution, I would say, well, maybe I can write some malicious program and put it somewhere downstream in this memory, and then I would let the user run his or her program naively. The user will happily run his program. The program will actually do what it's supposed to do, but then unknowingly the computer will continue executing, and then boom, my program will go to work and will start to do some bad things like deleting random files on the user's computer. So what can we do in order to avoid this potential problem? By the way, this particular attack is called NOP slide, and NOP stands for null instructions or null opcodes. And what we have here in instructions 6 onward are null instructions. And a bad hacker can use these instructions to slide the flow of control to an area of the memory that he controls, and then something bad can happen. What can we do to avert this problem? And in general, what can we do to terminate the program properly? Well, one thing that you have to understand is that computers never stand still. They always do something. Even when you don't touch the keyboard, there are many processes running in the background. So in the hack computer, because we don't want the computer to do something crazy, we might as well cause the computer to do something that we control. So what we can do is we can end the program with an infinite loop. We can add 2 commands like at 6 and then in 7 jump to 6. So we have, once again, at 6 and then in 7 jump to 6, jump 6, jump 6, and so on. And we have this infinite loop, and everything is under control because this is something that we intended our program to do. So as a best practice advice, we recommend that you end every one of your programs with an infinite loop. All right. Before the end of this unit, I'd like to say a few things about another feature of the language that we haven't yet discussed. And by saying this, I'm basically going to complete the specification of the hack machine language. The language features several built-in symbols, and here they are. First of all, we have a set of 16 so-called virtual registers, or to say it more accurately, we have a set of 16 labels that we use as if they represented virtual registers. And these labels range from R0 to R15, and the contract is such that whenever the assembler or the translator sees a label like R3, it will replace it with the number 3. That's all. So you may ask yourself, why do we need these fancy labels? Well, here's an example where these labels can come to play. This is a very simple piece of code in which we set RAM5 to 15. Now, let's read carefully what is going on here. In the first pair of instructions, we use the A register as a data register. We put the number 15 into A, and then we move it into D. In the second pair of instructions, we do something remarkably different. We use the et5 command to address the memory, to select memory register number 5. And then we do m equals d. So there's something troubling about this code. First of all, we do two very different things, but we use exactly the same syntax, et number. That's one thing which is a little bit, I think, disconcerting. And the other thing which is somewhat troubling is that when you read a single A instruction, you have no idea what the programmer wanted to do until you see the next instruction. So how can we make this thing more readable? Well, our advice is that whenever you want to address one of the first 16 registers in the memory, use the label convention, and then anyone who reads your program will know exactly what you want to do, including yourself, because machine. Our advice is that whenever you want to address one of the first 16 registers in the memory, use the label convention, and then anyone who reads your program will know exactly what you want to do, including yourself, because machine language programs are difficult to read and comprehend, and therefore we have to make every effort to make them more readable so that next time you see your program a week from now or 2 weeks from now, you will know what the program is doing. So in the second example that you see on the right, it's a very small difference compared to the left one, but it's much more readable. And also effectively, the program will do exactly the same thing, because once it will get translated, the R5 will change to 5, and then we are back to where we were before. So this is the motivation why we recommend to use these so-called virtual registers. There's one thing that you have to worry about, and this is the fact that, like many other programming languages, hex is case sensitive. And uppercase R5 is not the same as lowercase R5. And we recommend that you remember this observation here, because if you forget it, it can cause all sorts of very exotic bugs. And in the future, if you have a program that has no syntax problems and you have no idea what this program is doing, there's a good chance that you misspelled one of your symbols. So keep this in the back of your mind when you run your own symbolic programs. what other symbols do you have in the language? Well, we also have screen and keyboard, which we discussed previously in one of the units. They stand for the base addresses of the screen and the keyboard memory maps. And we also have a set of 6 additional symbols that we don't really use in this course. So let me wrap up the symbols, the built-in or the predefined symbols in the Hack language. We have 16 virtual registers. We have 2 symbols that stand for base addresses of input-output maps. And we have a set of 6 symbols which are used by people who want to write virtual machines and compilers for high-level languages that will operate on top of the Hack platform. Now, this is something that we actually do in the second part of this course, called NAND to Tetris Part 2, but we won't use these 6 registers in the present course. All right, so this has been a brief overview of working with registers and memory, and in the next unit, we're going to talk about branching, variables, and iteration. In the previous unit, we talked about working with registers and memory, which is the basis for doing everything in low-level machine language. And in this unit, we'll see things which are more familiar to high-level programmers, like branching. Interestingly enough, we can store it variables and iteration. So let us begin with. In the previous unit, we talked about working with registers and memory, which is the basis for doing everything in low-level machine language. And in this unit, we'll see things which are more familiar to high-level programmers, like branching, variables, and iteration. So let us begin with branching. Branching is this fundamental ability to tell the computer to evaluate a certain Boolean condition or Boolean expression, and based on this value, to decide whether or not we want to jump and execute some other section in our program, or simply move on and execute the next instruction in the program. Any programming language has various branching mechanisms. For example, if you write programs in Java or in Python, you have things like if, else, while, repeat, switch, and so on. In machine language, we typically have only one branching apparatus, and this thing is called goto. And here is how we use this goto in a particular example. In this program, we want to look at a certain data value and decide or determine whether or not this value is positive or not. So we decide, as a matter of convention, that the value will reside in RAM 0. So the user of this program has the responsibility of putting a value in RAM 0, and then when the user press execute, the program spins its wheels, and at the end of the execution, the program will put in R1, in RAM 1, either the value 1 if RAM 0 is positive, or the value 0 elsewhere. So this is the typical if-else, and unfortunately, we don't have a way to express this thing directly in low-level programming. Low-level programming is much more Spartan and minimal, and therefore we have to work hard to make this happen. In particular, here is some code that I've written to accomplish this this operation. It's probably not the only way to do it, but it works. And I've used red ink to highlight the areas of the code that actually refer to this computation of if R0 is greater than 0, set R1 to 1. Let us ignore the rest. Of the program for now. So in the two instructions 8 and 9, I'm taking care of setting R1 to 1. And in instructions 2 and 3, I check the value of the data input, which is now residing in D. And based on this value, I decide whether or not I want to jump to instruction number 8, in which I will actually set R1 to 1. Now, if you're not sure exactly how this thing works, I recommend that you stop the video and simply run this thing in your head or with a piece of paper and convince yourself that you understand how the branching is actually working here. Now, as a matter of experiment, let me remove the line numbers and also remove the documentation and just stare at this piece of code. And if I will also remove the preamble documentation, I would argue that what will remain is quite unreadable. This is an example of cryptic code, very difficult to understand what this code is trying to do. And yet, the code will work perfectly. This is a flawless program. If you will load it into the computer after you translate it into binary code, it will work perfectly. It will deliver the Signum abstraction. The user will be very happily, and yet the program is not readable. Now, this is a perfect point to invoke a quote by Donald Knuth, who said that instead of imagining that our main task as programmers is to instruct a computer what to do, let us concentrate rather on explaining to human beings, fellow programmers, what we intend the computer to do. This is super important because if we don't have this capability, if our programs will not be self-documenting, we won't be able to fix and extend them. All right, so what can we do to make this program more readable? Well, fortunately, we have a very nice feature in assembly languages, which is called symbolic references. So let's take a look at what I did here. I have introduced a label that I made up, and I decided to call it positive because it's a sensible choice of a label because it describes roughly what I'm trying to do. And this positive label appears twice in the code. In the first place that I want you to look at, I declare this label. And basically what I'm saying here is a piece of code that I want to jump to from some other place in the program. And I'm going to call this location in the code positive. And when we designed the Hack assembly language, we decided that label declarations will be made by just writing the label and enclosing it into round parentheses. So this is how we declare a label in the Hack assembly language, and this is how we use the label. So instead of saying at 8, we now say at positive. And it is the job of the assembler and the translator to translate these labels into concrete numbers. And let us observe how this actually takes place. So once again, the general rule is that at label will translate into at n, where n is the instruction number following the label declaration. Let us remember that instructions have implicit numbers, and here they are. So when I take this piece of code and I load it into the instruction memory, here's what happens. First of all, whoever makes the translation has to operate according to a certain contract. You know, if you write the assembler, for example, something we'll do in week 6, we will tell you that the language makes some assumptions and some conventions, and you have to write your assembler or to carry out the translation according to this contract. So first of all, notice that label declarations are not translated. Now we have two label declarations here, positive and end. One is just before line 8, and the other one is before line 10. They are not translated, they are ignored, and they generate no code, surprisingly enough. Okay, what about the references to the labels? Well, the references to the labels definitely get translated, and what used to be at positive becomes at 8, because 8 is the instruction just after positive, and what used to be at end becomes at 10 for the same reason. So the second part of our contract is that each reference to a label is replaced with a reference to the instruction number following that label's declaration. So once we keep this thing in mind, we can happily invent and use as many labels as we want in our program. And then we can use these labels to effect the notion of branching. Okay, so having dealt with branching, and obviously it's something that we'll return to because you cannot write any non-trivial program without branching, let's move on and talk about another abstraction called variables. All right, so what is a variable? A variable is an abstraction of a container that has a name and a value. And in high-level languages, we have different types of data, different types of variables, and yet in the low level of machine language, or at least in the low level of the Hack machine language, we have only one variable type. We have only 16-bit values to worry about. And this abstraction can be delivered or can be implemented by using a single register in our data memory. So we use single registers to represent every one of our variables if we want to create variables in our program. So here's an example in which variables come into play. And in this program, I want to flip the values of RAM0 and RAM1. And I do it using a classical programming idiom that appears in practically every basic programming course. I create a variable. Typically, we call it something like temp to denote the fact that it's a temporary variable, and I need it only for this purpose. And I do some manipulations that end up delivering the necessary flip operation. So the question is, how do you do it in machine language, where so far we didn't have the notion of variables, so this is a good opportunity to introduce them. Well, here's how I decided to do it. And let us focus only on the read instructions in this program. And in particular, in the first read instruction, I declare a variable called temp, and then I immediately go on to use it. Now, what is the meaning of this cryptic command at temp? And notice that unlike labels and references, we don't have a corresponding label called temp. So what do we mean when we say at temp like this? Well, here's what we mean. Basically, we present the following pledge to the computer. Please go to the memory unit, find some available memory register. Let us assume that it's register number n, and use it from now on to represent what I prefer to call the variable temp. So from now on, whenever you see a symbolic instruction at temp, I request that you treat it as if it were an at n instruction that we already know how to handle. Okay, so this is the meaning, or that's how I realize this variable abstraction. So let us observe what happens when you translate this program and load it into instruction memory. Well, the first observation is that when you look at the code, you see that what used to be at temp became at 16. And because at temp appears twice in the program, we have two occurrences of the at 16 instruction. So how does this happen? Well, whoever wrote the assembler or implemented this translator worked according to a contract that we, as the language designers, have put together. So the contract has two rules as follows. First of all, a reference to a symbol that has no corresponding label declaration is treated as a reference to a variable. We assume that the programmer wanted to create a variable. And the second rule is that variables are allocated to the RAM from address 16 onward. In this particular example, we have only one variable, so it ends up being allocated to RAM 16. If we'll have more variables in the program, we'll use RAM locations 17, 18, and so on and so forth. And practically, you can use as many variables as you want. And I can say it safely because typically, programmers use only half a dozen or a dozen variables or something like this. And in the Hack language, you can actually use thousands of variables, but no one actually comes up to this to so many variables. So in closing of this little section about variable, if you look at this piece of code, you will realize that this program is relatively easy to read and debug. We have a symbolic label, and we have a symbolic variable, temp, and it's much easier to understand what is going on here compared to the programs that we wrote before when we used actual numbers to represent addresses. This program has another very nice virtue, which is more subtle, and this is the fact that this program is what is known as relocatable code. I can take this program and load it into memory, not necessarily to address 0. I can put it anywhere I want in memory as long as I remember what is the base address that I use for this program. This is extremely important because, as you know, when you work with your personal computer, you typically have several programs executing at the same time. So you can imply from this that several programs are loaded into your main memory. And once we write these programs carefully using symbolic references, we don't have to worry about where they will be located in memory. We can write something called loader that takes care of this technical detail. So symbolic programs are good. The next programming idiom that I would like to discuss is iteration. So, for example, suppose we want to compute the sum of the series 1 plus 2 plus 3 all the way up to n, where n is some given input. How do we do it? Well, normally you use some accumulator variable to accumulate the running total of the series. So you set this variable to 0, and then you do 0 plus 1 gives you 1, 1 plus 2 gives you 3, 3 plus 3 gives you 6, and so on and so forth until you reach n. Now, if you have to write this program in low-level language, it always pays off to begin with some low-level oriented pseudocode. And this is what I did here. So once you convince yourself that this pseudocode actually delivers the required functionality, we can move on and translate this pseudocode on paper into symbolic machine language. So let us begin with the first part of this program, in which we declare and initialize the three variables n, I, and sum. So first of all, notice that there's a one-to-one mapping between the names of the variables that I use in my pseudocode to the names of variables in the symbolic language, which is kind of nice. So we have these three variables, and let us assume that I translate only this part of the program and load it into the instruction memory. Here is what I'm going to get. At n would be translated into at 16, at I into at 17, and at sum into at 18. This should not be surprising because it follows the contract that we discussed earlier. Variables are allocated to consecutive RAM addresses from 16 onward. All right, so let's keep this in mind and complete the translation of the pseudocode into machine language. The details of this program are not terribly important. Well, they are if you actually have to write this program, but they're not important to the things that I want to emphasize in this unit. But I do expect you to, once again, stop the video now and convince yourself that you understand what this code is doing. And by the way, when you write such a program, if I told you, if I gave you this program as an assignment, I highly recommend that you first write it in pseudocode, and then I recommend that you debug your pseudocode and convince yourself that the pseudocode actually works. And once you convince yourself that it works, you can reduce the task of writing the machine code to that of simply translating from pseudocode to machine language. And you see, this is much easier to do. You know, you look at the pseudo command like n equals r0, and you write a set of instructions in machine language that do the same. Or take a look at the instruction that follows the loop directive in the pseudocode. You know, it says if I is greater than n, go to stop. So it's much easier to simply focus on this instruction only and translate it into machine language. So this is one way to write a low-level code and convince yourself that it works. And the second way to verify that the code works, which is no less important, is once your program is written, you have to simulate it, or we recommend that you simulate it on paper, using some sort of what is known as a trace table. Now, a trace table is a piece of paper on which you write down the names of all the main players in your program, or the main variables of interest in your program, and then you record in the table the values of these programs throughout the program's execution. So these are the values of these variables of interest in iteration 0, and then you go through the loop and you figure out what happens after the first iteration, after the second iteration, the third iteration, and so on and so forth. Okay, so you do this for 3 or 4 iterations, and you try to convince yourself that the program is actually working. So in closing, here's our best practice advice for writing hack machine language programs. First of all, you have to design the program using some sort of pseudocode, and you can follow the pseudocode example that we used in the previous slide. Second, you have to take your pseudocode and re-express it using the hack assembly language. And finally, we recommend that you test this, the resulting program on paper using some sort of a trace table. And notice that I did all these things without touching the computer. Everything was done on paper, but actually I probably wrote the program using some text editor. But once again, a text editor for me is like using a piece of paper. And it's very important that you convince yourself that the program is working before you actually, you know, unleash it on the actual computer. All right, so this has been the unit in which we talked about branching variables, and iteration. And in the next unit, we are going to talk about pointers and input-output, and this will be the end of our coverage of low-level heck programming. Simultaneously. In the previous 2 units, we talked about working with registers and memory, branching, variables, iteration. And what remains to be done in order to complete our survey of hack programming is talk about how we handle something called pointers and how we write programs that manipulate our input and output devices. So that's what we'll do in the current unit. Let us begin with pointers. And as usual, I would like to start with an example in which pointers come to play. In particular, I want you to consider this very simple piece of code that many of you have written in, at least those of you who took programming courses before NAND to Tetris. So in this code segment, I manipulate an array called ARR. I assume that this array has been declared and initialized at some point. And now I write a piece of code that sets the first n entries of this array to the value -1. If you write with a regular high-level language, it's very easy to write such a statement, such a for statement. And as you know by now, when you have to bring it down to the level of machine language, you have to work much harder to deliver the required functionality. So how do we do it? Well, one thing that you have to realize, and in fact you realize it only when you set out to write a compiler, is that the notion of arrays gets lost in the translation, so to speak. So when the assembler has completed to translate this piece of code from, let's say, Java or Python into machine language, the machine language no longer recognizes the array abstraction. And as far as the machine language is concerned, the array is just a segment in memory of which we know the base address of this segment and the length of the array that the programmer has decided to declare. So if we assume that the array starts in address 100 and that we want to do something to the first 10 entries of this array, this is how it's going to look like in the data memory on which memory. Of which we know the base address of this segment and the length of the array that the programmer has decided to declare. So if we assume that the array starts in address 100 and that we want to do something to the first 10 entries of this array, this is how it's going to look like in the data memory on which this program will end up executing. We start with 2 variables. One of them holds the base address of the array, and the other one is the number of entries that we want to manipulate. And what we would like to see is that at the end of the execution of this program, we would like to see the first 10 entries of this array set to -1. This is the goal. That's what we want to do. And the question is, of course, how do we actually do it? All right, so let's start working on this on writing this particular program. The beginning of the program is going to set up these variables that we just discussed. So we assign the number 100 to ARR to signify that the array ARR begins in the memory register number 100. And we do something similar with n. We assign the number 10 to n. We initialize I to 0. Once again, don't forget, we're trying to deliver the functionality of a for loop that begins with I equals 0. So we set I to 0, and then we can start actually going through the loop, so to speak. So once we do these three variable declarations and assignments, we have this setting ARR, end, and I allocated to memory registers 16, 17, and 18, and we are ready to begin the actual processing. All right, so here is the actual processing. The first segment of the loop, and by the way, we realize the for loop using a machine language oriented loop, which begins with a label declaration called a loop. And the first thing that we do is we translate the termination condition into a machine language. So what used to be if I equals n, go to end, which is the end of the processing, because once I, what is I? I begins with 0 and goes through 1, 2, 3. When it gets to 10 in our example, we want to jump to end. So we have 6 hack instructions that actually perform this semantics. And then we come to the heart of this. Loop in which we actually assign the number -1, which is meaningless, by the way. We just use it as an example. We assign -1 to the current entry of the array. How do we do it? Well, let us begin with a comment. As you see, what we are doing is we are computing the value of ARR plus I, which is the value of the base address of this array plus the current value of the index. Now, if the index begins with 0, then the first entry that we're going to operate on is RAM 100, because ARR is 100. And then I will become 1, so we'll operate on RAM 101, and then I becomes 2, we'll operate on RAM 102, and so on and so forth. How do we do it? Well, we have to add up ARR and I, and that's exactly what we do in the first 4 instructions. We say at ARR, we address the variable called ARR. We put the value of this variable in D. Then we say at I, we address the variable I. We add up D plus M, and we put the result in the A register. Now, this is something which is new to, should be new to you, because it's the first time that we actually use this capability of the language to assign something directly to A using an arithmetic operation. Okay? Now, what will happen when we do it? Well, D plus M now store an address. So this address is assigned to A, and by the time we say M equals -1, the register that will be affected is the register that A addresses. Now, if we do this within a loop that runs 10 times or 10,000 times, in each iteration, the A register will acquire one more address, and we're going to operate on a different register in the memory. And that's exactly what we want to do. So after we run so many iterations, we'll get the desired effect. And as usual, we recommend that you stop the video and convince yourself that this is actually working as advertised. So variables that store memory addresses like ARR and I are called pointers in any language, not only in Hack. And in Hack, the typical logic is as follows. Whenever we have to access memory using a pointer, we need some instructions like A equals something that comes from some memory register. So the typical semantics is set the address register to the value of some memory register in which I do some pointer arithmetic to compute the address on which I want to operate. Okay, so this, in a nutshell, is how we do pointer processing in the Hack machine language. In the next part of this unit, in the next and final part of this unit, we will see how pointer manipulation comes to play in the when we write code that interacts with the screen and with other similar peripheral devices. All right, so so let's talk about input-output. First of all, if you recall, we have two
Todo por ahí.